Now, another sort of almost philosophical question about this, what is the purpose of the derivative block here in the context of this whole control system? I would say it converts the raw data from the sensor, or data from whatever input we're getting, into another form that is the data that or the quantity that we're actually trying to control, which is velocity, right? We're saying, okay, we've already taken into account the position, but we want to directly control the velocity. So we need to take our input and convert it, like do some mathematical transformation to get the velocity so we can control it. Keep that in mind. Okay, completely different scenario for using feedback loops now. Moving the robot around the field. Kind of important, right? The robot needs to move to different points in the field. So let's come up with a scenario to show how we would do that. A couple points on here. That's straight up, that's straight to the right. Say this is the current position of the robot, including its orientation. That's the target where we want it to be, including the orientation. How do we go about doing this? First of all, what's all the intermediate? This is a representation of states of the robot, right? Point with an arrow. What are sort of all the intermediate states? I mean, we could have some arc like that, where we're driving forward while turning right. Maybe depending on the type of drive we have, if we can move in any direction, not just forwards or backwards while turning, maybe we move straight to the target while turning. Maybe, for whatever reason, we decide it's more beneficial to kind of more sweep in that way while turning. Point is, there's different ways we can get to the target. That's a non-trivial question. Do we necessarily care what path we take? Most of the time, yes. What if there's a thing here that we can't drive through? A thing there that we can't drive through? What if, in the case of next drive, sure, it can move in any direction, but it's faster at moving forwards, backwards, left, or right than it is moving on any diagonal. We probably want to take that into consideration if we're trying to do this motion as fast as possible. So that's a question that sort of needs to be in the back of our mind when coming up with a control system to get the robot to do this. What sensors do we have in the robot? Let's just say, for the sake of simplicity, for a first example, that our next drive has 4 wheels like that, each with a motor on it. Every single motor also has an encoder in it. An encoder tells us the current position, and then we can take the derivative of that to get velocity, etc. So let's say we have just, these 4 wheels, we have an encoder on each telling us the current position of that wheel. Let's say we have that information. What's one way that we could get to this? Well, let's say arcs are hard. Let's look at this one. Maybe we, step 1, turn 45 degrees to the right. Step 2, go forward approximately 28 units, whatever units we chose to use for position and distance. And another 45-degree turn to the right. That's one way of getting there, right? How do you do this? Well, you can figure out how to make this kind of drive turn on the spot. You send that wheel that way, that way, that way, and that way. The robot will turn, right? So assume this is just one output that you're sending the same value to every wheel, and your input is maybe the position of one of the wheels. You've done the math based on the radius here. You know how far the wheel has to turn to get the robot to turn 45 degrees, etc. So you now have a target for where that needs to be. You have an input, and you have enough to build up a PID loop for that, right? Similar idea for driving forward. On X drive, that's what driving forward looks like. Same idea, you can pick any one of these encoders, and you could, use that as an input, do the math to figure out how much it would need to turn for the robot to drive perfectly forward 28 inches, and you could build up a PID loop, right? So you could run your turning one until it's very close to 45 degrees. You could run this one until it's very close to 28, and then you could run the turning one again until it's very close to 45 degrees, zeroing out the sensor between each step, right? That's one way to do it. There's one key word that I used a few times here, and that's very close. That's 2 words. Very close. Turn until you're very close to 45 degrees. Drive forward until you're very close to 28 inches. Turn until you're very close to 45 degrees again. How close is very close? How close is close enough? Let's say you were half a degree off on this turn, which by the way is impressive in its own right. So you're half a degree off. How far off will you be when you get there, assuming that the straight drive goes perfectly? Well, I can do, the answer is 28 times the tangent, in degrees, of 0.5, which is about a quarter of an inch. Okay, that's not too bad. What if I change that to 1 degree? About half an inch. Makes sense. Is half an inch too much to be off? It entirely depends on the scenario. Maybe that's good enough. What if you weren't just driving? 28 inches is like that much. It's a little over 2 feet, right? The field is 12 feet by 12 feet. What if you're driving across the field? If you were 1 degree off, you can get about 5 inches off. Is 5 inches too much? Well, when your bot is maybe, what if we're talking about a smaller robot is 15 inches wide? Being 5 inches off, that, depending on what it needs to do, that could be very significant, right? So so that's one issue with it. Another one. In that we talk about only one particular type of error, which is just not going far enough, or maybe slightly overshooting, right? How do we know that the robot's going to turn around its center? Ideally, if all 4 motors spin at the exact same velocity, their velocity with respect to time curves look identical, yes, it will spin around the center and it will drive perfectly straight forward. Unlikely. What? That requires, first of all, that all 4 motors and gears and bearings and wheels are identical, have identical defects, because there's no such thing as a part with absolutely 0 defects, etc. It also would require that the center of mass of the robot be precisely over the center of your chassis. Also very unlikely, especially if you could be picking things up and putting them down as you're driving around, right? So that's probably not going to happen. So that is another thing. So maybe as we're turning, we're slightly drifting off by an inch maybe. As we're driving forward, maybe while accelerating, the left side is able to accelerate a bit faster than the right side because there's a lot of weight on the right side of the robot. Now not only are we not driving, well, now we're not driving perfectly straight for the first bit, which means actually we'll curve to the right a bit, and we won't even know it when we get there. So what is a better way? Remember that derivative block that I was talking about on the last one? Everyone remember what I said for what its purpose was? To convert the data into the format, or into the quantities that we're actually trying to control. When we're doing this, are we trying to control the exact amount of turning the front left wheel on the robot does? No, that's not the quantity that we're trying to control. What are we trying to control? The robot's position and the robot's orientation. I won't go through the exact math as to how we get the position and orientation data from whatever sensors we may have on the robot. However, assume that we have some sensors. This isn't necessarily one real number. You can have that can be any data type. That can be either like a set of numbers, like from multiple sensors or whatever. Just putting that out there. Let's assume we have some function which converts that into x, y orientation. Right? Call this, maybe this is the corner of the field, maybe that's origin, this is the x-axis, y-axis. Call this is 0, right? That's positive, normal convention for angles and x and y, right? So let's say we get out of f, I do this a little close to the top of the screen. Say this is x, this is y, and this is theta. And then, what can we do? We can run, I'm not going to write in the targets here, but we can run a PID loop. My apologies for that being small, but believe me, they all say PID in them. We can run a PID loop on each of them, right? Because we're trying to get theta, being the orientation, to a certain value. Theta is initially pi over 2, we want to get to 0. X is initially 10, we want it to be 30. Y is initially 20, we want it to be 40, right? So that's a perfect scenario where we could use PID. And the interesting thing here, and sorry, let's assume we have some other function, g, for example, that converts these three numbers into 4 voltages to send to the motors, right? Then we have our control loop, our feedback loop, right? Does that make sense? Now there are more complicated ways of doing this, so like come up with an optimal path, figure out what the fastest way of getting there is, figure out how we can go around an obstacle if we have one, etc. But in principle, this works, right? Given that we have this f and this g, does this make sense to everyone?
Is g like a real function, or is it like something that kind of gets there? Like, can we actually
G? Oh no, g is okay. I can do g. G is relatively simple. So there's 2 stages to this. I'll do the second stage first because it'll make a bit more sense. We have these numbers. Okay, this is v sub x, v sub y, and v sub theta. What they are is v sub x is how, like, some representation of how much power we want moving right, or if it's negative, moving left. V sub y is how much power moving forward, or if it's negative, moving backward. And v sub theta is how much power we want turning one way or another. We'll call one positive, one negative, right? Now, VFL, I'll keep these direction notations for what positive means. VFR, VBL, VBR for the voltages. Why did I put F? VFR. For the voltages, this time the motors on the front left, front right, back left, and back right wheels. Okay, those are our variables. The simplest way to do this is VFL, and I'll just write out and then I'll explain it. So VFL. Okay, so first of all, how do you come up with this? If Vy is positive, which way do we want this spinning? That way, right? Vy is negative, we want spinning that way. So coefficient on that is positive. X, if x is positive, we want that spinning that way. So coefficient on x is positive. If v theta is positive, we want that going backwards, right? So coefficient on there is negative. Do that for each one, you end up with this. Does that make sense? Cool. And the other, I don't know if I want to do a rigorous proof for it, but yes, you can just add all that up, and it works. The issue here is that there's a maximum voltage that you can apply across the motor. That's the voltage of the battery. Often what we'll do is this won't actually be voltage, it'll be percentage of the maximum voltage. Or proportion, meaning that like 1 means full throttle, right? So if 1 means full throttle, what do you do if one or more of these adds up to more than 1? If you don't do anything, what the underlying system between like our code and the motors does is if it's more than 1, it just assumes it's 1. it's less than -1, it assumes it's -1. So it just caps it to the range -1 to 1. Okay? Where that becomes an issue is then some of these get scaled down, but they don't all get scaled down. Because if we just multiplied everything here by some constant, it would still represent the same motion, just slower, right? But if some of them get changed, but others stay the same, then either we're representing a slightly different motion, so it's moving in a bit of a different direction if we're on a diagonal, or maybe it's like, yeah, something like that. And also, you'll notice something else here. This is a linear transformation from 3 variables to 4 variables. Meaning that, if for those of you who have taken linear algebra, what can you tell me about the output set? Not every combination of 4 numbers is in it, right? Not every possible set of 4 numbers is going to be produced by putting a set of 3 numbers through a linear transformation, right? So, but if you start arbitrarily changing the outputs, then you could end up with one of those 4, like one of those sets of 4 numbers that's not in the output set of this. What does that mean physically? It means that your wheels are driving against each other. It means that, because technically, so an X drive can move forwards, backwards, that's 1 degree of freedom, left, right, that's another degree of freedom, and it can turn, that's a 3rd degree of freedom. Technically, you can create a 4th degree of freedom if you make your drive be able to expand or contract in 1 dimension. That's what it's trying to do if you pick something that's not in that input set. It's trying to pull the drive apart or push it together.
For example, if you powered the front wheels forwards and the back wheels backwards, it would try and stretch.
Yeah, it would try and stretch or compress this way. Pull it that way, compress this way, it's identical. So that's not what you want to do. So typically what we'll do is if this, we'll do everything nicely, but if somehow this, any one of these adds up to more than 1, or less than -1, we take the greatest absolute value and divide all of them by it, so that the greatest, the largest one is 1, or -1. Make sense? Okay, so that's the second half. So that's how we get, if we have this, like if we have an x, y, and theta, and remember x represents left, right, y represents forward, backwards, theta represents turning. That's how we turn that into motor velocities. There's one other step that needs to happen in G though, because we can't just plug this into there. Can anyone tell me why? Okay, if we want the robot to go that way, we'll have a large positive value here from y, right? If we plug a large value into here, what does that do to the robot? It goes forwards. Which way is forwards? Depends on the orientation. So, you take the 2D vector represented by x and y, and you rotate it by negative of the orientation. So, if it is, the orientation is, say, that way, that's pi over 4, right? Rotated by negative pi over 4, meaning it gets rotated that way. So if our, let's say we came up with like x equals 0, y equals 1, just as a simple case. Rotate by negative 45, we get negative 45 degrees. You get x equals 1 over root 2, y equals 1 over root 2, and, okay, never mind, it's rotated the other way, so that would actually be negative, my bad. So you rotate it by a positive value of theta. You get, basically, this telling you to go equal amounts left and forward. If this went equal amounts left and forward, which way would it move? Vector x equals 0, y equals 1, rotated it by theta equal, like the direction that the robot's facing is pi by 4. Rotate by that. That means taking this vector, rotating it that way by 45 degrees. You get something that's negative on x, positive on y. This moves, the robot's here, and it moves negative on x, positive on y. Equal amounts, that means it's relative to the robot, it's moving that way, right? If it's moving that way, it's moving in the direction we want, which is in the positive y-axis. So what we do, to recap, we take the movement in what we call global x and y, that our PID gives us. We rotate that by the current orientation of the robot to get what we would call local X and Y. And we put that through this linear transformation to get actual motor voltages. And then as a final step, we make sure that none of them are going to get capped down. So if the largest one is greater than 1, we scale them all down. Make sense? Cool. And I believe that's as far as I want to go.